All right, how's everyone doing today? And getting used to the 3-day weekends? I could get used to that. So first order of business, there's rumors that this group is going to be back on campus tomorrow to do another thing. So obviously if people don't want to come to campus, right, everything's recorded and there's nothing, pop quiz or anything like that going on. So, do whatever you have to do.
When do we have a midterm?
I think it's a week from Friday. Check Canvas.
It's on 9?
2 weeks? Okay. Yeah, it's pretty far out. But 2:15 if you're in there, midterm is this Friday. All right. Did anybody lose an earring last week? It's a little hard to see. There you go. Anyway, been sitting here. I'm guessing.
Right there?
Yeah, it might be Heidi's, but I don't know. We'll see. I'm guessing it's not Scott's because it's still here. All right. Yes.
While we're asking about the midterm, I noticed that it has like a pretty extensive buffer of notes. You can bring in like 4 pages or something like
Yeah,
that.
I think 4 double-sided pages.
So that's kind of like intimidating. Is there like different study methods that are effective?
So I don't think you need 8 single-sided pages of notes for the midterm. I make that limit high because I don't want it to be a limiting factor. But I don't want to say open book, open note, because then people bring in a 1,000-page Unix manual and start flipping through it like crazy because they never thought about what should I actually learn for the exam, right? But I don't think you're going to need 8 pages of notes, okay? I just want you to have plenty if you want to write big or you feel like there's things you want to put down and so on.
So studying our ODPs and our programming.
ODPs, programming assignments, are going to be excellent ways to study because most of the midterm is going to be writing pieces of code. Probably not writing entire programs, really writing, write a function that does this, write a snippet of code that does that. So things along those lines. If you can do the ODPs, if the programming assignments are making sense, you're in pretty good shape. Yeah?
Are we going to have something like a study guide?
Yeah. It's forever in the future, though. We don't have to worry about it for a long time. But yeah, I'll post up a list of topics and problems to think about and stuff like that when it gets closer. Remember, whatever I ask you to do on the midterm, I have to grade 65 times. So that limits how much I'm going to ask you to do. Not seriously, but usually I'm looking for basic programming constructs. Can you code a while loop? So I'll ask you to do something that requires looping inside a while statement, things like that.
Both Bash and C.
Yeah. So it'll be both Bash programming and C programming.
And something like holiday program.
Yeah, something like the ODPs. Those are always good. Same level of depth for what I'm looking for on tests usually, yeah. All right, so I posted an ODP. I didn't get this up till 9 this morning. But this is ODP 413, so we're back to C code. And I want you to write a function named count_e, which counts the number of e's in a string. So, coincidence, I know. So, integer count_e. And the prototype I specify is a character star. We're going to talk about this for a few minutes. But count_e, you should pass it a string, okay, which is an array of characters. And it should go through and count the number of lowercase e's and then return that number as the function value. And as usual, count_e doesn't print anything. It doesn't ask for any input. It just takes the argument. Yeah?
So should we just do 100 characters?
you don't have to specify the length, because when you write your function, you're going to say the argument is a char star. Okay, but we do have to know how far we have to look through this string, and there's two ways to do that. So we're going to go over that as well. So it accepts a string, counts the number of times lowercase e occurs in the string, returns that as its value. And the rest is kind of boilerplate, right? Put your function in a file called count.e.c. Write your own main function, so read from standard in if you like, get a string, pass it to count e, print out the value, right? So you can test it, make sure it works with an empty string, make sure it works with a string that has no e's, a string that has only e's, and everything in between. And then when you're ready to assess, compile it with that file from /temp odp413 main, and go ahead and assess. If you use string functions like string length, you want to include string.h in angle brackets, so that's mentioned up there. There's two sort of general ways to go about string processing. One is kind of the barehanded approach. The other is to use some of these functions like string length and string compare that come from string.h. So let's talk a little bit about strings and make sure we're all on common footing here. So this is a function prototype, right? In prototypes, we don't usually name the variables and the arguments. We're just saying what types of arguments are. But you could put a name in here. It doesn't do anything, but it does no harm. But if you're actually writing your function, you name your variable as usual. I'm just going to call it str for string. Now, in our main program, we might do something like this. Right, and this is just a test program, so I can say I'm only going to test it with strings up to 100. That's not limiting how big a string count e can work with. Okay, if I took this from argv bracket 1, there'd be no effective limit on the length. But I'm just going to make an array that's 100 characters long, and I'm going to say fgets data 100 standard in. And I'm going to print a prompt to say, please enter a string containing some e's, etc. And then I want to call my function, so I'm going to say integer c equals count e. And here, I'm just going to say data, the name of my array. And I'm going to print c and do whatever else. So there's a little bit of a difference in how things look when we're calling versus how they look when we're writing the function, right? When we're calling, we pass the name of the array. Okay, and here we declared this array by char variable name bracket size. In some cases, you might see this declared up here as a char star data, or it might come from argv bracket 1, where argv was a char star star, right? There's lots of different ways we can declare this variable that we're passing, but the important thing is whatever we use in here has got to ultimately be a pointer to a character. It's got to be a character array.
If you use char star and you do fgets in, what would be the value for, like, so there you have 100. What would you use for star? Or what would be the limit for it?
That's an excellent question. So let's suppose that in your main program we do this. So this is suppose. And it's written in red. That's caution. So we'll do a char star data, and we'll say fgets data and something and standard in. So what's the reasonable value to put in this question mark? What's a safe value?
0 is the only safe value.
0 is the only safe value. Okay, if we try to do this when we've said data is a pointer to a character, we don't know where data is pointing, right? We've told the compiler it's going to point to a character, so it will be happy when we put it here, but it's not actually pointing anywhere in particular. It's got random stuff in it. And pretty much no matter what we do, when we run this fgets, we're going to get a seg fault. Okay, so this is where we get into the dreaded Malloc statements. So we could say something like data equals Malloc 200. And now Malloc is finding 200 bytes of memory somewhere. It's saying data should point to those 200 bytes, and now we could put a 200 in here safely. But unless you go through all of that, including the Malloc call, right, we don't usually want to declare a variable to be a char star if we're responsible for setting up that variable. Now when we're writing count E, we're not responsible for giving str a value. That's going to be passed to us, right? So we're okay saying char star str because we trust that whoever passes this argument to us has done the right thing. For example, made data an array of 100 characters and then passed the address of that first character. So we'll get into mallocs later, but for now I'm going to say when you're trying to make an array, right, do it like this, right, where you actually declare the size of it. Does that make sense?
Does the compiler return that one into the malloc?
No, it doesn't actually call malloc. It takes the memory from somewhere else. Malloc pulls storage off of what we call the heap. It's like a big general data structure we can pull memory out of. This will, I think, place it on the stack. I'm not positive. But you can try both versions in GDB and see what the address of data is. It'd be interesting. All right, so count E, we're going to pass a char star. But inside here, str is a character array. Str is also a string. And the assumption here, whenever we talk about passing strings, is that these are null terminated strings. So one of the things about C is arrays don't have a natural length associated with them. We can make an array of 100 characters and call it data, but if I pass that to a function, there's no way that this function knows how big that array is. It's not part of C. It's not part of assembly language either. So if we just start chowing on this memory location and start looking for E's, we don't know when to stop, right? There's nothing about an array that naturally tells you how big it is. So there's a convention in C that when we have character arrays, we terminate them with this \0, this null character.
And fgets automatically puts that at the end, right?
And fgets puts that at the end. Most things put that at the end. And if we believe that this is always the way that strings are terminated, right, then everything kind of works really well for us. But it's just a convention, right? There's nothing inherent about a character array that says you got to have a null terminator somewhere. And that's a really common bug sometimes when you're working with these strings by hand. Sometimes you forget to make sure there's a null terminator, and your code ends up like doing crazy things, and usually seg faults, or prints off gibberish and then seg faults. All right, so we can think of this argument as a character array, or we can think of it as a string. Okay. But either way, it's an array, which means when we're inside here, we can do things like str bracket 0, and that'll get us the first character of that string, or str bracket 1, or more generally str bracket I. So we can access the characters of this array using an integer index, which means we can throw this in a for loop or a while loop or whatever else we need. And we know that if string bracket I is equal to this null terminator, then I has reached the end of the string, right? So if we're looping through inside a while loop or something, we could loop until string bracket I is equal to a null terminator. And this thing, by the way, single quotes are used to represent a character. Double quotes are used to represent a string. So this is basically the number 65. It's the ASCII code for an A. It's an integer. Whereas this is some big, long, crazy memory location, probably starting with 7FFF. And at that location, we would find a 65 followed by a 0, which is the null terminator. All right, so this is a string of one character containing an A. This is just an integer containing the ASCII code for A. Okay, totally different creatures. And if I do something like see if string bracket I is equal to double quote backslash 0, it's never going to be equal. And I'll end up flying off the end of my array and getting seg faults. So when you're looking for a lowercase e, you definitely want to look for that. Okay, double quotes will give you something crazy. ASCII codes is really bad practice. Don't embed ASCII codes in here. Because this may not be running on a computer that uses ASCII. It could be using EBCDIC or Unicode or something different. And the compiler will turn that into the proper internal code for an E for whatever system you're running on. Yeah?
So for double quotes, it's really mean the memory address.
Double quotes exactly means the memory address.
Can we compare like a variable memory address with a double quotes memory address? Is that compare address with address?
Yeah, so let's try that. So let's just read in two strings using fgets, and let's compare them. All right, so hello, bye are definitely not the same. Hello, hello are also not the same. So let's GDB it. And I'm going to put a breakpoint at line 9. So when I get down to that if statement, I can stop the action and take a look at what's inside my buffers. So I'm going to say continue, enter first string hello, enter second string hello. All right, so buff 1 is this, buff 2 is that, and they're certainly the same up to the null terminator, but they're not going to print out as equal. So this equals equals operator in C is pretty crude. It's really just comparing bit patterns. So let me throw in a printf. I'm going to print these out in hex. And the compiler is going to complain because it knows buff1 is a pointer, but I don't care. I'm just going to print out the value of buff1 and buff2. And so here's what we see. Buff1 is this address that ends with FD0. Buff2 is this address that ends with 050. And by the time this is compiled and is running on the CPU as machine code, when it says is buff1 equal to buff2, it's going to look at these two values and say, no, they're different. All right, and it's not going to look at the fact that they're pointing to something that has the same null terminated string. So there's a difference here between comparing buff1 and buff2, which are memory addresses, right, and comparing the things at those memory addresses. So if we want to actually compare the things at those memory addresses, we can use a function like string compare. So string compare is a function we can get to its prototype through string.h. And this does what we normally want to do when we compare strings. It will look at the thing pointed to by each string, and then we'll start marching through character by character up to the null terminator. And if they're both the same length and all the characters match, it will return a 0, which tells us these are the same strings. Let me save the value from string comp. And if they're not the same, I'm just going to print out what that value was that came back from string comp, which we know is not going to be 0. So if I do hello and hello, string comp will tell me these are the same strings. If I do hello and goodbye, string comp returns something non-zero. In fact, it returned a 1. If I do hello and ha-ha, it returns a 4. Again, the question here is it 0 or non-zero? If it's non-zero, they're different, but it's not always going to be 1, it's not always going to be 4, it's not always going to be positive. If I do ha-ha and hello, it returns a -4. So it's actually comparing two strings alphabetically. And the minus is telling me that the first string comes before the second string alphabetically. So the H's match, but then the A comes 4 positions before an E, that's the -4. So string comp we can use not just to compare, but also to alphabetize if we like.
When you say 4 positions before, is that looking at the ASCII code?
Looking at the ASCII codes, yeah. All right, so we got one way to go through a string, which is to use an index, and we could loop while the string at that index is not equal to the null terminator. And that'll get us through character by character, and you can use that to count E's and so on. The other is to use a function called string length. And string length takes a string and tells you how many characters are in it. And it does not count the null terminator. Okay, it goes up to and including the last character before that. And so if we wanted to use a for loop, we could go for I equals 0, I less than string length of string I plus plus. So test code, let's make a string of 120 characters. Let's use an fgets. Let's print out string length. That's weird. I'm gonna ignore that. So I'll put in hello, and it tells me string length is equal to 6, which is pretty close. I'll put in hi, it tells me string length is 3. I'll put in nothing, and it tells me string length is 1.
It includes the null terminator in the count.
Almost. It's not including the null terminator, but it's including the new line, right? So when you hit enter, it puts a new line in there, and that gets tacked on. And if I hit Control D to signal end a file, it came back with a 0, but that might not always happen. But it basically didn't load anything into that string, and it had a null terminator sitting in the beginning apparently. So let's play with these. So I'm going to loop through all the characters. Now, if string length is equal to 5, it means I have characters 0, 1, 2, 3, and 4 in my array. So I'm going to let I be less than 5, but I'm not going to take it up to 5, because 5 would technically be outside my array. I'm going to go from 0 while it's less than string length. I'm just going to print out my index and say character index equals, going to print out the value of that character as an integer, and then I'm going to print out the value of that character as a character. That's what the %C will do. And I'll just throw some double quotes in there and put it in parentheses. So let's put in hello. And so it's showing me what each of my characters is equal to. The first number is the ASCII code. And then in parentheses, I see the actual character in double quotes, and you can clearly see the new line here, right? Character 10 is a new line character, Control J, and then it shows me quote, and it jumps down to a new line. So what if I went one further? What if I went less than or equal to string length?
You want to print the null terminator?
That should print the null terminator. So character 6 is a 0, and it prints as just nothing. What if I go beyond that?
It would say fault or gibberish.
Probably gibberish, but segfault's always a good possibility. Oh, they all turn out to be null. That's kind of nice. But if we go too far beyond, we might get our seg fault. Nope. You got a big block of memory there. That's interesting. Try one more. Gotta get one seg fault per lecture. There we go.
Okay.
So 6,000 bytes later, it hit a section of memory it didn't have access to. All right. This is debugging nightmare if you've got something like that, because it might work great, right? Until I run it, and for some reason I give it 7,000 characters of input, and then it like gets unhappy. We got into some good stuff though here. Yeah, there's a lot of good stuff in memory here. So where does all this stuff come from? I mean, it's not gibberish, right?
There's str, which is what you
There's
executed.
str, which is the program name. There's xdg. There's session ID.
Could this be assembly
term.
language?
Next term.
Xterm, SSH client. We're reading environment variables in here, right? So when you set up things like your prompt, or when you change your directory, and you have a different current working directory, that stuff gets stored in memory. Well, we're tapping into that here, right? /dev/pts/0 tells you what device I'm running on, right? It's just sitting in the computer's memory. But the program that's running has no idea that it's no longer looking at part of my character array, right? It's just reading successive memory locations, and it's stumbling into some operating system stuff, which is kind of cool, but could also be kind of scary, right? So /home/Nick, well, that's my home directory. My language is English, EN_US, right? So we're just snooping around the memory here. And eventually, if we snoop too far, this is my IP address, 192.102.5, right? So this stuff is out there. And that can be useful, or it can be a security issue, yeah. And then at some point we hit something that was protected from our access.
Good to hear.
Yeah. All right, so let's see, where does this leave us? So this is a reasonable way to go through a for loop. Right? Just go while you're less than string length. Or we could do this as a while loop. So I'll initialize I to 0, and while that character of string is not the null terminator, we can go ahead and print out the character and the index.
You need to increment it.
Oh, and I always forget to increment in while loops. You can tell I don't use while loops. Thank you. All right, so that does the same thing as before. Could I do this I++ somewhere up here? Just part of the reason of I++ is so you can put it inside other statements. But which one of these would I put it on? The first one or the second one or the third one? I have no idea.
It shouldn't matter, should it? Because it won't even go and check it for the while it goes through.
I think it will mess it up big time if we do the wrong one.
It might just do LO.
Yeah. So I would not do this, right? There's probably a way to make it work, but it's probably compiler dependent. But here's the idea. Suppose I do this. which says let's print out the value of I and then the value of string bracket I and the value of string bracket I, and then when we're done, let's go ahead and increment I, right, to avoid having to put that I++ on the next line. But we're assuming that it's going to do something with this last string bracket I at the very end. That may or may not be the case. I'm kind of curious now. That seemed to work. No, it didn't seem to work. Because it started off and it said character 1 equals H. Character 2 equals E. Yeah. And yeah, 101's not right either because that's the ASCII code for E, and 108 is the ASCII code for L. Because it claims L is both 108 and 111. So don't do this, but I'm pretty sure the first one is the one that gets evaluated first. So that looks more normal. But a different compiler might do different things, because the order in which these things are pushed on the stack might be compiler dependent. So do an I++ down there. Does it matter if I do I++ or ++I?
Yes.
Yeah?
Either way.
Depending on where you put it.
If I put it right here.
Ish, I don't think so.
Since you're not using the incremented LP, so
Yeah, I'm not using the incremented value, so it doesn't really matter if I say ++ or ++I or I++. Right? It makes a difference if I said something like x equals, and then it says, do I want to increment before or after the assignment?
Do we have to count capital E's?
Nope. Lowercase. All right, so yeah, let's see if we've left anything untouched on here. I think that's all good. Yeah, number of times a lowercase e. All right, so partial overview, maybe not completely, but hopefully that gives you some start on dealing with strings as arguments, right? So pass in a char star, but even inside a function where you're passing a char star, right? This is just an array, so you can say string bracket, right? And you can say string length, whatever that argument is. You can say string length of str. And it's just an array, so string length will go through and look for the null terminator. You can use string compare, all these other things, right? So character arrays, strings, same thing. All right, is that enough to do the ODP, you think? Maybe.
I hope so.
Okay. Hope's good. All right, so PA2 I graded up, and that looked really good. So people's games played well. A bunch of people forgot to put in a comment block in the beginning, though, with their name and assignment and description of the program, and I really hate taking off points for that. Because a lot of the people who did that had like a perfect program other than that. You gotta, at the very least, put your name somewhere in your code, okay? But definitely just whatever your main program is, throw in a block of code at the top. You can make this once and stick it in a file and just copy and paste it and change the details, right? In fact, most modern tools will do that for you automatically when you go into something. If you did 250 and you use some of the HDL tools, right? They always throw a block of comments in the front with the date and your name and some spaces where you can fill in details, right? So you can make yourself something like that and just include it in your code. A few cases where the error handling was not quite what it was supposed to be, where you were not kicking out if there was an invalid command line argument, or you weren't repeatedly trying for how many sticks you want to take, things like that. But other than those, most people, their programs played great. Had a few talking cows, which was nice. So yeah, so really good work on PA2. Much better than I've seen in past years as far as where people are, as far as C programming and algorithms and things like that. I think you're on solid foundation here, which is great, because it's going to let us just keep building on top of that. So so PA3, a little different algorithm for the high-low game, and shell script instead of C, but I don't think anyone's going to have a huge issue getting that done either. And then PA4 will come up with something good to do. So keep rocking on that. So let me talk a little more about this thing I keep talking about, which is modularization. And modularization is hard to say. Is this idea of breaking things into pieces. So here's a version of the stick game that I put together. So how many sticks would you like to play with? Blah, right? Error must be positive integer. How many sticks would you like to play with? 21. So it shows me the sticks. How many do you want to take? I'm going to be mean to my computer. I'm going to win. All right. So the way I've written this is with a bunch of functions. And the reason I did this, and I do not have my name in here, so don't laugh at me. The reason I did this is because it makes my main program trivial. Here, I'll put my initials in. My main program is nothing, right? I declare numsticks to be an integer. I pass argc argv to start, that was an ODP, to see how many sticks I want to play with. And start will either return the legal valid number of sticks the user requested, or it'll give me a flag by returning a 0 saying something went wrong, we're giving up on this user. So I set numsticks equal to start, and I can say if numsticks equals 0, return 1. And then I show the number of sticks that you have, so I print out the little collection of sticks with the number in parentheses, and then I play the game with that many sticks, and then I return a 0. So I write, 6 or 7 lines of code, my main program's done.
In play game, did you have other functions within play game?
Oh yeah. Yeah, play game's the real workhorse, right? That's where all the kind of heavy lifting happens. And that's going to call a bunch of other functions, right? But we do this anyway, right? When we're writing, I got a message. When we're writing code, we call things like string length, right? Why? Because we don't want to write code in here that says how many characters long is this. So we pass that request to a function called string length. When we want to print something, we don't break this up into characters and convert this number into ASCII codes, right? We just call this function printf. So we're using this idea of modularization all the time, but we're going to use it with some code that we write ourselves. Hello. All right, so start was an ODP, and it's actually a fairly gross function. Because it's got all these different cases, right? If there's more than 2 arguments, I just say too many arguments and we're done. If there's exactly argc is equal to 2, then there's exactly 2 things on the command line, program name and argument. So we take argv, we scan it. If it doesn't scan successfully, we say error, that's not an integer. Otherwise, we take the value that it's saved, which is in numsticks, and we say is that positive, and if it's not, print an error message and we leave. Otherwise, we just return that value of numsticks. And then we got to do the same thing if argc was equal to 1, but this time we have to prompt for how many sticks, read it with an fgets, and then do the scanf, see if it's invalid, and if it is, return our flag of 0, otherwise return numsticks. So that's lots of kind of ugly, detail-oriented, nitpicky, what does this person want on this assignment and why is it different from PA1 kind of details, right? But it's all buried inside this one function. And inside main, all I know is I'm just going to call this start function, and it's going to either give me back a 0 saying something went wrong, goodbye, or it's going to tell me how many sticks to play with. And if something's wrong with the way I did this, if I test it and it's not doing the right thing, right, I can come back in here and I can tweak this and I can test this and so on and so forth. All right, and then show sticks is pretty straightforward, right? You tell it how many sticks you want to show, it prints out that many pipes and then prints out that number in parentheses. But there's lots of places where you want to show sticks, the beginning of the game, after the user moves, after the computer moves, and I don't want to write this code 3 times. So put it in a function. And then there's play game. Play game's shorter than start. So tell it how many sticks you're playing with, and I have a while loop while num sticks is bigger than 0, but that while loop doesn't actually do anything because I exit whenever the game's over. But see how many sticks the user wants to take. And this deals with all the issues of print out a message, do an fgets, see if it's an integer, see if it's 1, 2, or 3, right? That's all buried inside here. And get user move will keep prompting the user and keep trying to get input and parse it until it gets a number that's valid, and it returns that, and now user I know is either a 1, 2, or a 3. So I subtract that from the number of sticks, and if the number of sticks is not positive, game's over and the user won because they just moved, and now the sticks are all gone. And I return. Otherwise, I show the number of sticks, and then figure out the computer's move. So find the number of sticks mod 4. If that's equal to 0, have the computer take 1 stick. Tell the user the computer takes %d sticks, and this just puts out an S if the number is bigger than 1, just using the ternary operator. Subtract that number of sticks from num sticks, and if that goes less than or equal to 0, say the computer won. Otherwise, show the number of sticks, and then go back up to the top of the while loop. And so we never actually come out of the while loop at the bottom. We just return.
If you were writing, let's say you're working for like a company, for example, and you're writing code, would you want your main program to be pretty much just functions? Or like
It kind of depends on the company and the year and that kind of stuff. But by and large, a lot of times main programs are really just a bunch of top-level function calls. Not always, right? You got to kind of do what makes sense. But typically, yeah, that would be pretty common. But I don't know if it's necessarily like a specification requirement that a company would have. But it's not uncommon. So the last function is this get user move, and this isn't too bad, but it deals with all this foolishness of repeatedly asking the user what they want to do. So I just have a do more flag that starts off at 1, and while that's set, ask how many sticks they want to take, get their input, scan it as an integer. If it doesn't scan successfully or that integer is out of range, print an error message and continue. Otherwise, clear my do more flag, which gets me out of the while loop, and then return num. I could have just returned num from right here, but it felt like I was never leaving my while loop, so I decided to use a flag instead. So we'll start from this tomorrow. I want to look at this thing called stick.h and talk about what that's doing in here. This is our function prototyping, why we have that up there, and then I want to talk about different ways to compile this and build this up, and we're going to lead up to the idea of make files. So that's where we're heading tomorrow and maybe Thursday. All right, I'll see you next time.